But we just put it here into the assumption. Now, here are the natural assumptions. Just take any bounded subinterval of your time of definition. And then you want to have that here, sort of the measures in space-time are locally bounded, integrating over a compact set. And we have local L2 bounds on the mean curvature in space-time. And we have seen that's the very natural assumption, just by monotonicity of area. So this gives kind of control on the area. And now we want to see we want to have mean curvature flow. We call what is the idea? If you have a smooth mean curvature flow, then if you just integrate against the test function and you differentiate, then you get the first term you get is the derivative of the measure, this mean curvature squared times the test function. Then you have to differentiate the test function in space, and then you get how the points are moving. That's mean curvature. And sure, if it depends the test function explicitly on time, you also need to differentiate in time. Okay, but so what we do now for Brakke flow, you integrate this. This means you would get this equality, this statement here, but with equality here. And that would first think, okay, that's maybe most natural definition for a weak mean curvature flow. And as we have discussed last time, one has to actually put in here an inequality, just out of the reason that we'll see today, that if you hope to get any good compactness statements, we have to allow that if you have a sequence of flows, that in the limit this L2 integral on the mean curvature jumps down, just because we have only, in some sense, weak convergence of the mean curvature for almost every time. And as we have seen, like if you have weak convergence of functions, let's say with bounded L2 norm, then just by duality, the L2 norm can jump down in the limit, because there can be oscillations, so things can be can oscillate out. Okay, now are there any questions so far with the definition before we continue? Okay, and if I don't hear anything, here's a second part of this remark. So this is also kind of a weak strong uniqueness. So assume that MT is a smooth family of hypersurfaces so which satisfies just this inequality here, this integrated, assume you have a smooth evolution, but you don't know its mean curvature flow yet, but it satisfies this here, then one can show that so if you have a smooth flow and you have just the definition of Brakke flow, then it has to be a smooth mean curvature flow. We'll see one way of proving this later. It's true in any codimension, but at least if you see, although we put this inequality in, since we're allowing to test with any test function, that gives us in the end enough information to say it has to be a mean curvature flow. So at least that is good. So here's the first very basic theorem. What is the most basic thing? We want to prove local area bounds. Okay, so mu t, t in I, and integral. I'll be writing n dimensional because we're restricting to this, but it works in any codimension. Just don't want to write always codimension on Rn plus 1. Then we take the following test function, r squared minus modulus of x squared minus 2nt. And we take the positive part. And if you have to think about it, in some sense, this is a test function which resembles the evolution of a shrinking sphere. If you remember, this was exactly what was inside how the radius changes of an evolving sphere. Okay, then if you take phi to the 4, actually phi cubed would also work, just to make it smoother. See, this is only Lipschitz here because you take only the positive part, so we have to take a power to make it smooth enough. Is decreasing in t. So this means we get local area control. See, it's a positive test function, The support will shrink, but this gives us local control. Here's the proof, and the proof is easy, but maybe interesting to see how you do something like this. Just take f is 1/4 phi to the fourth, just to make it a bit nicer. Then the gradient of f in the ambient is phi cubed grad phi. And so what do we get? If you want to compute the divergence along a surface of gradient of f, now you see the first term is here when the divergence hits this phi cubed, but then this gives just a tangential gradient, 3 phi squared grad tangential phi norm squared plus phi cubed divergence of grad phi. Now look at grad phi. So what is grad phi? This is just minus 2x. And if you check, the divergence of the position vector field is always the dimension. So what do we get here is you can estimate this from below. This is greater or equal minus 2n phi cubed. We drop the first term, and this comes from that term, comes exactly from this part. Okay. Now let's compute the time derivative. Moreover, df by dt is phi cubed, d phi by dt is minus 2n phi cubed. Okay, and you already see these two terms here, they fit together nicely. Now, what you do is now apply the Brakke flow definition. To exactly this test function f. So what do we get? We get integral over f d mu b minus integral f d mu a. We integrate from a to b is less or equal than integral from a to b. Integral minus mean curvature norm squared plus with grad f plus df by dt d mu t dt. Okay, this is just the definition. Okay, so we drop this term. This is a negative term. But you see this term, we can just use the divergence theorem, just integrate by parts. We have no boundary. That was the assumption that for almost every time we have a weak mean curvature, we can integrate by parts. So we get here that this is less or equal, dropping the first term, to minus the divergence of m over grad f plus df by dt d mu t dt, and that's by our computation less or equal than 0. Everyone happy with this? So see, here we use the divergence theorem which we stated last time, remember? So our assumption is we have no singular part, so more or less our varifold for almost every time has no boundary. It's in the definition of so we have a weak mean curvature, so we can use the definition of the weak mean curvature to more or less integrate by parts here, to use the divergence structure of the mean curvature. So, and then we just put in our estimate that's less or equal to 0. And that gives us a local estimate. So this means, you see here, this is a positive test function. You see, the test function is concentrating down, it gets smaller, and the support is shrinking, But if you control the area on a little bit bigger ball, then you control it on a smaller ball at later times, Very typical for parabolic equation. You have an energy control on a little bit bigger ball at some time. Now we wait a little bit, and then you get an energy control on a smaller ball at a later time. Okay, so what is the corollary for an integral n-dimensional Brakke flow? Mu t on Rn plus 1 defined on an interval AB. We have a compact set we have uniform mass bounds i.e. there is ck independent of t, such that, but it depends on this interval ab, yeah, that mu t of k is less than some number ck is less than infinity for all t in ab. So where does this come from? So see, we had here in the definition, we had here this number 1, yeah. This means if we integrate over this over any compact set, then for almost every time this has to be finite. No, it's a Radon measure. Yeah? Or it's just a Radon measure. It has to be a Radon measure, but we can just now more or less what we do, you enlarge the set K a little bit, just make it a little bit bigger, and take many slices in time very close to each other, make it a bit bigger, use the shrinking test function, and then you get a control on a smaller set, but where you have filled in the gaps in time. So that we can take a set, we cover it with a lot of balls, we go a little bit forward in time, we get a little bit smaller set, which we still cover, but we get full control out of just that time, and now we just need to take finitely many time slices where we assume control, and then we get uniform control for all times. Yeah, there is some control, so this is a natural thing that you get this for Brakke flows. Yeah. Okay, now here's the next important thing. Yeah, a question? Okay. An integral Brakke flow satisfies for a compact set compactly contained, or set compactly contained in Rn plus 1, that you get a mean curvature squared bounds. Yeah. C of k 1 plus b minus a. Okay, well, this is not exactly the same C as before, huh? Let's call it C prime here, yeah. And we'll see later how this looks like. Here's the proof. Huh? Okay, now you take a test function in C2C, n plus 1. You assume it's non-negative, time independent. Now recall there's this very basic estimate that you can estimate grad phi squared over phi always by a constant which only depends on the second derivatives of phi. Yeah? There's this little analysis trick. I guess a lot of you will have seen that. Yeah, if not, it's an exercise. Since now, see, the problem is in the definition of Brakke flow here. Yeah, I see this looks good here. This term looks good, but we need to control this term. Yeah? When someone want to use that term to estimate, to sort of take care of that term here. So that's what we do here now. Now we have grad phi scalar product with mean curvature. This is definitely less than 1/2 grad phi squared over phi plus 1/2 phi times mean curvature squared. Important, but you should always note that function still is a smooth function with compact support. Yeah, although it looks funny, it's still a smooth function with compact support. Yeah, so we can use it always also as a test function, or at least when we look at convergences. Yeah, so we have the following now: integral phi d mu b minus integral phi d mu a is greater or equal integral a to b, just the definition of Brakke flow, phi times mean curvature vector squared minus grad phi times scalar product with mean curvature d mu t dt. Remember, we have no time dependence. Okay, now we just use this estimate from above, and we can estimate this, that this is greater or equal to 1/2 phi mean curvature squared minus 1/2 grad phi squared over phi d mu t dt. Okay, now let's rearrange this. So we see integral a to b, integral 1/2 phi, what is h squared d mu t dt. This is less or equal from phi d mu A minus phi d mu B plus 1/2 integral A to B grad phi squared over phi d mu t dt is less than phi d mu A minus phi d mu B plus, okay, now here's this constant which just depends on phi, yeah? This was exactly that constant from here, yeah? Times integral A to B. Now you integrate now just over the characteristic function of the support of phi. Just make it as an estimate from above, yeah? Okay, so this is then we can write this as this is some constant c of phi times c of k times 1 plus b minus a, where we have assumed that phi has support in k. Okay, and we see that gives this nice estimate.
So don't you mean that phi is equal to 1 in k or something?
No, we just choose this in that way.
Okay,
yeah.
Because if it's sort of if the support is, it should be the other way around, right?
Yeah, just choose phi in the right way. Okay.
Yeah.
Now phi is not 1 in k. You have to take k a little bit bigger, and then you have to take this ck prime a tiny, like twice of k or something like this. Yeah. Yeah, you enlarge k a little bit. See.
I mean, you in the statement of the theorem, you want an estimate for the integral over k, right? So you.
Yeah, but this is not the same. You see, this is a different.
This is not the same k. Okay.
Yeah, it's not the same. You can always adjust it in that way.
Right. So you take the support of the test function bigger than the support of the domain in the theorem.
Yeah. So where the function is 1, that sort of you take k where the function is 1, yeah, and then you just make a cutoff. Yeah.
Yeah. Right.
Yeah, you're right. Okay. Now, here is another theorem which is sort of important here. There's kind of a local monotonicity of area also in the measure sense, yeah? And or like an upper semi-continuity, an integral n-dimensional Brakke flow satisfies the following. That won't be so important in the end, but it's a good statement. And then you'll see that the technique we use is actually will be what we'll need later. Huh? That if you take limit, if you go from smaller times to over mu t, mu tau here, that this is bigger or equal than mu t. This is greater or equal to, if you come from positive times down to t, from bigger times down to t, mu tau, i.e., what we want to have here, just let's spell this out for a test function. We need a sign on the test function, otherwise this does not work. Okay, let's do a proof here. So the statement in the end is we don't need that so much. We won't need it, but more or less the way of proving is what the important thing later is. Yeah. Assume first that phi, so we assume a bit more regular C2C. General case follows by approximation. So if a test function which is only C0C, we can just mollify it a little bit and use the mollified one instead. Yeah? Then, okay, just the statement again. Phi d mu d minus phi d mu c is less than integral c to d minus phi times h squared plus h grad phi. Again, this is definition. We are time independent. Okay, now let's just do the thing what we did before. Huh? So this is less or equal to C2D, 1/2 grad phi squared over phi d mu t dt. Huh? So we split this term up how we did before. Huh? Now, as we had seen before, we can estimate this by some constant depending on phi, but now this time is correct. Yeah, thank you for reminding me, Mario, but this time is correct. C of phi times this constant C support phi, where K we can now take equal to the support here, times D minus C. Okay, do you agree, Mario? Is this?
Yeah, yes.
This is okay now? No?
Yes.
Yeah. So the important thing is, this is an important observation. If you look at the following function, this will be one of the main tools here. And if you listen to things what Richard does for Brakke flow, for Ricci flow, for weak Ricci flow, it does exactly the same thing. Yeah? He has an almost monotone local quantity that gives him the whole control. Yeah? The same thing here. So this is the corresponding quantity here. D mu t minus, so you call this whole thing, this is C of phi, C support phi times t. This is decreasing in t. So for Ricci flow, this is sort of this kind of local entropy there, what he uses. Yeah, it's the replacement here. So what does this mean? This means f of t minus is always greater or equal than f of t is greater or equal than f of t plus. Okay. This finishes the proof. As the linear part of f is continuous. See, if you look at this here, this linear part, that's continuous. So this means if there are jumps, the jumps can only happen in that part. And that gives you this statement here. And you can, you first prove it for C2C, and then you see this here is, you can now approximate. This is a monotone function, and then you can get it for you get this monotonicity for any C2C function. Then you approximate a C2C function, C0 function by C2 function. You still get the same monotonicity. Okay, but the important corollary here is, and this is the tool we'll be using today a lot for the compactness, for an integral n-dimensional Brakke flow in Rn+1, and we have a test function in C2C. The following map, T maps to phi d mu t minus C of phi C support phi, where this is, so I mean by support by this is the set K I'm looking at, times t is decreasing in t. Okay? That's what we used. That was the whole tool. This will be the main tool in getting compactness. Okay, any questions so far? Okay, let's do compactness. Okay, here's the theorem. And the important thing is to note, think maybe first of smooth mean curvature flows, and you realize the assumption is the completely natural assumption. Yeah? Suppose you have a sequence mu it is a sequence of integral Brakke flows on Rn+1. Now, what is the most natural assumption? That the area bounds are locally uniform. Assume the bounds on area are locally uniform. i.e., what do we want to have? We want to have, if we take the supremum in I, the supremum over T in AB, over mu IT of K, that's less than some constant C of K is less than infinity for all K which are compactly contained in Rn plus 1. Huh? Does everyone agree? This is the most natural assumption. We just want uniform control on the areas. And the statement is that is enough. See, this is why this is so powerful. Huh? Because it's really compactness under the natural assumption on an energy control. Then after passing to a subsequence, we have that mu IT converges as Radon measures to some limited family of limited Radon measures for all T in AB. So we get a family of Radon measures in the limit to this is an integral Brakke flow. But note here, in this statement, there's no uniformity in time. There's no uniformity of the convergence. It's really pointwise convergence. Like in time, it's pointwise. Okay, but you can improve a little bit the behavior in time. Yeah. Now, you want to have that really some of surfaces are converging for almost every T in AB. Now, the annoying part or the important part after passing to a further subsequence which depends on T, the associated manifolds converge nicely, i.e. VIT converges weakly to VT. So this means you can pick almost every time, and then if you have picked the time, you have to choose another subsequence, and then you get manifold convergence. But the subsequence depends on the time which you have chosen. So this is a bit annoying, but you see where it comes in. It comes from using Fatou's lemma. So let's do the proof. Are there other questions with the statement of the theorem before we start with the proof? No? So really the important thing is to think about this is really completely natural. No? This is why this is so helpful later. We don't need any curvature bounds or anything. We just use area bounds. No? So, okay. Choose a test function in C2C. Phi non-negative. Yeah. Now recall alpha I of T look at this function. This is a sequence of uniformly bounded decreasing functions of T. Now, okay, what happens if you have a sequence of decreasing functions? You want to extract a limit, they're bounded. Now think about if you have a sequence of decreasing functions, you can now take a countable dense subset. You can get a limit on this countable dense subset, sure, by taking a subsequence, because the functions are bounded. Yeah? But the function you will then define on this countable dense subset in the limit will also be a decreasing function. But if you know you have a decreasing function can have only countably many jump times. At all the other points, a decreasing function has to be continuous. So this means away from a countable set of times, the limiting function is continuous. So you can just fill in, away from this countable set of times, you can fill in the limiting function. And now in this, you have a countable set of times where you don't have convergence. So we can choose this further subsequence to get convergence on this countable set of times as well. Yeah? And if you look, this is also what Richard uses for Ricci flow. Yeah? a similar argument. Okay, so passing to a subsequence, depending on phi, we have that L phi I of t converges pointwise to a decreasing function L of t. Little exercise, I just explained how it goes. Hence, this here, remember we just add this linear part here, huh? So this means this here has a limit for all t in AB. Okay, but you know, for every, we have now one fixed subsequence, we have fixed the limit for this test function. Now what you first do is we now choose a countable then subset. Let's call this script S in C0C. Important, this is a separable space. Plus of functions, we can even make them a bit nicer. We can make them in C2C. Yeah? Functions in C2C, for example, just modify them a tiny bit. Or plus, repeating the above process for each phi in S. So S. Then choosing a diagonal subsequence, diagonal subsequence, we see that there is a subsequence in I such that for all phi in S, integral phi d mu it has a limit. For all t in AB. Okay, but remember this set S was a dense subset. You see this is uniformly continuous here, just depends on the difference of the test functions. So this means by density, this extends to all of C0C of Rn plus 1 R plus. That's great, huh? So now we have fixed the limit. Now we can put in more or less any positive test function. We know what the limit has to be, since the limits are unique. They're now fixed, are unique. We have that mu it converges to a unique limit mu t, which is a radon measure for a family of radon measures AB. Okay, and you see the whole game here to get this is really this local monotonicity. That's the whole game here. That's what you play with, So okay, now we're already pretty good, We have already gotten that we have convergence for all times, And what is our aim now for the rest here? Show that this is a Brakke flow and show strengthened convergence. Before we continue with this, are there any questions regarding this first part of the proof? No? Okay. Now, let's do a tiny little trick just to make the, not that I don't have to write so much. Now, replace the ambient space Rn plus 1 just by some open set U compactly contained in Rn plus 1 for simplicity. U open. So this means we may assume that we always have finite total measure. Yeah? We may assume that UIT of U is less or equal than C is less than infinity, independent of I and T. Yeah? If you want to do this in the end for the whole space, you just take an exhaustive sequence of open sets U and then argue on there. So it works as well there. Huh? Now, we have also shown that we can assume that now remember this was this first bound, integral a to b, integral mean curvature squared d mu it dt is less than d is less than infinity. Remember that's what we can assume. Remember this was this local space-time bound, independent of I, important. Remember for that we only needed the local area bounds. Now take, let's say, take CD contained in AB. Then, okay, what do we get from the definition? Sorry, D is greater or equal integral C to D. Can we just put the definition in curvature I norm squared minus grad phi in curvature I minus d phi dt d mu it dt. Okay, now let's just rewrite this in a funny way, So let's do this on the next page. So phi d mu ic minus phi d mu I d, now plus epsilon d, plus integral c to d, integral 1 over 2 epsilon. I'm just adding something on the left and right. You see it will be helpful. This is greater or equal than c to d. Right. And curvature squared minus grad phi h plus epsilon hi squared plus 1 over 2 epsilon grad phi squared minus d phi dt d mu it dt. Okay, I've just added more or less. I've added this term and this term on the left and right, and on the left side I've estimated this term from above by epsilon times d. Okay, that's what I did. Nothing deep. Okay, but now the good thing is, now recall, since we can estimate grad phi hi by just 1 over 2 epsilon grad phi squared plus epsilon over 2 norm hi squared. So what do we get? So we get that this term here actually phi h squared minus grad phi h plus epsilon hi squared plus 1 over 2 epsilon grad phi squared, that's greater or equal than epsilon over 2 norm hi squared is greater or equal than 0. So that's the first important. So you see, now this integrand on the right-hand side dominates a multiple of the mean curvature squared. And important, it has a sign. And if you recall now, because why I'm saying this, because we have to use Fatou's lemma. Now, so pass to a limit in I and use Fatou's lemma to see that Okay, see, so this term converges. This term converges. You see, this integral converges as well because we have convergence for f for each fixed time. Yeah, so by the dominated convergence theorem, this converges to the limit. Yeah, because the integral in t, this is bounded for each t. Yeah? And we have more or less in t pointwise convergence. So dominated convergence theorem gives us convergence of this. So we see that integral phi d mu t d mu c minus phi d mu d plus epsilon times d plus c to d integral over 1 over 2 epsilon grad phi squared d mu t dt. Oh, that's great. That's nicely convergence. That's great. We go, but okay, see, here we don't have convergence. So here we have to use Fatou's lemma. For that term, we have convergence. That term and that term, we have nice convergence. But we don't even mind for that so much. So we see we have C to D. Now here we have to use Fatou's lemma, lim inf in I. If we do this for HT separately, that's Fatou's lemma, but that's why we need the positivity. Phi times HI squared minus grad phi HI plus epsilon norm HI squared plus 1 over 2 epsilon grad phi squared d mu t dt. And now we have a nicely convergent term C to D d phi by dt d mu t dt. Okay. So what does this mean? Yeah. So this means especially that for almost every t in CD, we have that C of t. This is just the lim inf in I of exactly that integral phi times in curvature squared minus grad phi h plus epsilon hi squared plus 1 over 2 epsilon grad phi squared d mu t is less than infinity, because otherwise this couldn't be integrable. Has to be finite for almost every time, just by Lebesgue integration. So this lim inf has to be finite. Okay, but this is good, because this means for almost every time there's a subsequence that this is finite. We have seen this, it dominates mean curvature squared. So for almost every time, we can find at the time a subsequence where integral mean curvature squared is controlled. So pass to a subsequence. Depending on t. It's important. So this becomes a limit. Rather than a lim inf. Okay, we can do this. Since the integrand is bounded below by epsilon over 2 hi norm squared, we see that the mu it, it's now the sequence, are integral varifolds with mean curvature uniformly in L2 of mu t. Now, remember, L2 dominates L1, and remember that's what we need for Allard's theorem, Hence, we can apply Allard's theorem. There's we need a slightly strengthened version, which is in the notes, slightly, but it's very minor, it's just a technical thing to see in the notes, More or less, it's really Allard's theorem, to pass to a subsequence such that VIT converges to a limiting integral varifold, where VT is an integral varifold it has a weak mean curvature in L2 and no singular part. That's what you get of this being in L2, because this being in L2 means it's always absolutely continuous with respect to the mass measure. Yeah, that's what you get out of there. In particular, let's can check this in the strengthened version. In particular, we have that HI, if we integrate against any test vector field, d mu I vt. Remember, then we can integrate by parts. Just use the divergence. This converges to h x d mu vt. That's great. For x, the test vector field. The continuous vector field. Okay. Now here you can ask yourself, okay, is this now, we have chosen a subsequence. Here's the little note, yeah. For almost every t, yeah, v of t is well defined, independent of the subsequence dependent on t. Why is this true? This is because the mass measure, if we have a radon measure which comes from an integral varifold, then that uniquely defines the varifold. This is because an integral varifold, more or less the tangent space is uniquely defined and the multiplicity. Varifold V is uniquely defined by its associated measure mu v. Okay. Now we can return to C of t. Returning to C of t. Remember, this was this here. Okay. See, in this limit, now we get the convergence of that term. But remember, mean curvature only converges weakly. See, this is what we get here. This is weak convergence. See, we instead of we integrate against the test function. So we can just use duality, and duality implies that the L2 norm is lower semi-continuous in the limit. It can jump down. Okay. So this is exactly where we, for compactness, we need this. Returning to C of t, each term converges nicely to what we expect, except for the hi squared terms, which might drop in general. By weak convergence, just use duality. See, this was this here. This is weak convergence only. Now we integrate against something. Just use the duality. So hence we see that C of t is always greater or equal than integral phi mean curvature squared minus grad phi mean curvature plus epsilon mean curvature squared plus 1 over 2 epsilon grad phi squared d mu t. Now we're in the limit. See, now we have said, okay, we can't extract the limit really, but at least we have this inequality. Now what we do, you just cancel the terms with 1 over 2 epsilon grad phi squared on the left and right. On left-hand side and right-hand side. So this, remember that term also appeared on the right-hand side, integrated in time. Now we had on the left-hand side, we had epsilon times d, and we have epsilon h, where we just send epsilon to 0. After we cancel these two terms, we'll send epsilon to 0 and we're done. Yeah, and letting epsilon go to 0, we see that mu t is a Brakke flow. Okay, and that's the compactness theorem. Yeah. So, are there questions? I know this is all technical and difficult, huh? Yeah, so the trick is first you use this local monotonicity to get limits as measures, as Radon measures. And then you use this the defining equation for Brakke flow. Yeah, this is what we do here. Yeah, this is the defining equation. We play a bit around. Yeah, so we use this equation here. Yeah, that's what we use. We somehow say, okay, we should get a space-time integral mean curvature squared bound term. Yeah, by kind of doing Peter and Paul with this term. So that's what we do by just sort of playing around, adding the right term, which we then can control. Yeah, and the idea is then to use Fatou's lemma here. That's the trick. Huh? And the trick is then, okay, so you take the limit inferior here. You see this, then we can make sure that this then converges. Yeah? So this jumps down here, this converges, then we're done. And we get the Brakke flow in the limit. And then you see here, if you look at this, if you have this in the limit, this is converging, then you can just cancel these two terms. And then you just let epsilon go to 0 to cancel these two terms. Very nice. And we have the Brakke inequality in the limit. Okay. But you see, this is rather powerful. Yeah? And so, for example, why is this powerful? Yeah? Now, this means we can take limits. I guess if you know minimal surfaces, you know, for example, if you have a sequence of minimal surfaces, even smooth ones, yeah, or weak minimal surfaces, they converge to a limit, and you know the limit is smooth in multiplicity 1, then the convergence is smooth. That's Allard's regularity theorem. Something similar holds true for Brakke flows as well. I won't be able to cover this, but for example, if you know the limit is smooth, then you can make the convergence smooth. Then you know the convergence is smooth. So this means if you take any kind of geometric limit and you can, out of some other way, argue that the limit is smooth and nice, then the convergence is smooth and you get much better properties without first making in the blow up or in the convergence having to assume that you have control on curvatures or anything. So this is one of these really powerful tools for this. Okay. Now in the last half hour, I guess we can start a bit talking about elliptic regularization. Because this is sort of now really a little bit of break here. Are there any other questions regarding this?
Sorry, don't you need also to know something about the multiplicity for the regularity? Like
yes, if you know that the limit is smooth and it has multiplicity 1.
Yeah, okay, sure.
Yeah, sure, of course.
Yeah, is anything known if you have higher multiplicity? Or?
No, nothing is known.
Yeah, okay.
No, as the same as for minimal surfaces.
Yeah, of course. Yeah.
And you don't have like any notion of stability or something like this. Like for minimal surfaces, if you have stability and you have higher multiplicity, then at least sort of for like if you're below dimension 6, you get cheating away from a finitely number of points. If you're kind of like, for example, bounded genus in dimension 2 or finite total curvature or stuff like that. But that's not known for mean curvature flow.
Yeah, sure. So there is no analogy for stability. Like
no, that's the problem.
Yeah.
No? It's a gradient flow. There's been an open question for a long time. Is there any idea what should be a stable flow?
Yeah.
It's a very good question. It's a very good open question. Is there any way to understand what is a state? Is there any way to characterize, sort of give a class of weak flows which have somewhat better regularity, sort of like as you look at sort of for stable or finite index minimal surfaces?
So there's been like research for that, say, like to find a way to do that, to deal with that.
Say again?
So there is research in that path.
I think no one has come up with a good way. You just have you have to do other ways, yeah. But there's no direct replacement, unfortunately.
Yeah, but it's something that people have wondered, yeah, because I was asking
myself. Yeah, no, sure. People have wondered about this. Huh?
Yeah.
Is there? No? Okay. Any other questions? Okay, then let's start with existence, and this is sort of where the power of this So this is sort of something which is, if you compare it to Ricci flow, this is still completely open for Ricci flow. Existence by elliptic regularization. Okay, so this goes back to work of Ilmanen in '94. The paper is elliptic regularization and partial regularity for motion by mean curvature. I think it's in the notices of the AMS. I'm not wrong. Okay. So here, first observation. So our main idea will be, okay, I'll start the setup. It's better to explain then later what the idea is. Let's do the first following thing. Let's Z denote the height function in Rn plus 2. So we're extending the dimension by 1. We're taking Rn plus 1 cross R. We're adding an additional dimension, and E, the upward pointing unit vector, in this additional R direction here, okay? Then following statement, then M in Rn plus 2 is a, so this is an n plus 1 dimensional hypersurface, is a critical point of the following weighted area functional of integral m e to the minus lambda z dA if and only if t maps to m minus lambda t times e. So you see, solves mean curvature flow. So what is this? You see, you just take this fixed surface and just translate it down with speed lambda in this e direction. So this means this m is a critical point for this functional if and only if it defines a translating solution to mean curvature flow. Okay, let's prove this. So let S maps to MS be a variation of M with velocity x. So this is the velocity vector field. When we all know how to do this, then we compute the first variation, d by ds of ms e to the minus lambda s, dA at s equal to 0 is just mean curvature vector plus grad perp, that's a little exercise, minus lambda z times x e to the minus lambda z dA. And we can rewrite this as minus h minus lambda e perp. Just take the normal gradient times x e to the minus lambda z dA. See, what is the Euler-Lagrange equation? Is exactly that this vanishes, so that the mean curvature vector is equal to minus lambda times e perp. Now, on the other hand, t maps to m minus lambda t times e has velocity minus lambda e, and thus, remember, for mean curvature flow, we only need the normal velocity, and thus normal velocity minus lambda e perp. that has to be the mean curvature, yeah? Comparing, yeah, yields the statement. Okay, we exactly get, you see, this is exactly the defining equation for a translating solution to mean curvature flow, the translator. So what is the setup now? I'll try to explain this now. Okay. Just a quick question. Is this clear to everyone? Why this gives us a translator? Oh, I just see in the chat that someone asking if this is a bed behind me. Yes, it's a bed behind me because I'm in a shared house, not a shared house, a guest house at the University of Warwick, which is not used at the moment due to Corona. And that house has different rooms and also has here this office. But since they usually rent it out to more than only one person, they have put a bed into the office. So I have a bed in my office, okay? I can also sleep on it. Okay, now let's explain the setup. Now, what do you want to do?
There is another question in the chat. It says if E is a unit vector field.
Sorry, say again?
Is E a unit vector field?
Yes,
That's
yes.
another
E's
question.
unit.
Okay.
E's unit. E's unit, yes. Yes, thank you. Okay, now take sigma n as our initial surface that we want to flow. Huh? Where we want to construct a weak solution starting at this one. So this is our initial surface. It sits in Rn plus 1, but we want to actually be in Rn plus 2, so we put it in Rn plus 1 times 0 at height 0, and think of this sitting in Rn plus 1 cross R. I'll draw a picture in a moment. Okay, so we put it in the height 0, z equal to 0 slice. Okay, we want to have it closed. Okay, that's natural, and we let now the interesting thing is this defines a nice elliptic functional. You can actually prove it's in a conformally deformed metric. This is just an area functional in a conformally deformed metric. So the idea is this is a nice functional which you can minimize. Yeah, we let m lambda in Rn plus 2 minimize integral e to the minus lambda z dA subject to a boundary subject to dm lambda is equal to sigma. Okay, for yes, you need orientation, so we actually have to assume that sigma is orientable. But if you're in codimension 1 and closed, we are orientable. So to do all this, you have to work actually with currents. I'm not going into currents now, but just for you to know, if you know minimal surfaces, you can find a minimizer here. Okay, you can minimize. Yeah, there is a minimizer. Yeah, and I'll show in a moment how they look like. So can show, since these are minimizers now, that these m lambda exist. And in nice situations, i.e., for example, for hypersurfaces, are smooth away from a small singular set. Just a normal thing of codimension 6. Codimension 6 singular set. So thus we get T maps to m lambda minus lambda TE. We call this here m lambda T is a, say, smooth, very regular mean curvature flow. Okay, let's draw a picture. So what is the picture here? So we have down here, we have Rn plus 1. Here we have the additional z direction. There's an additional r direction. Here we have our initial surface. Let's put this here. This is our initial surface, sigma. Okay. Now, if you look at this functional, you see this weight of the functional here is decreasing as you go up in Z. You think of lambda being positive. Yeah? And you see if you make lambda more and more positive, yeah, then it's actually much better to go higher up. You want to span this boundary. We want to span this boundary, but we pay less if we go high up. If we make lambda big, we pay less by first going up and then actually bridging there and going back down. Okay, so what the effect will be is that these minimizers, they always lie in the upper half plane. You can prove this, yeah, just by a barrier principle. I don't want to do this. Yeah. They somehow kind of look like this. And the bigger you make lambda, the higher they get stretched up. And the idea is, as you let lambda go to infinity, so these are then defined translating solutions to mean curvature flow. You can kind of think you have this cylinder here. Here's kind of this cylinder over our initial data. Yeah, see? So this solid cylinder, yeah. So these solutions here define smooth translating solutions in the cylinder over sigma. Or maybe it can even go outside. It's not mean convex, so it can also go outside. Huh? Yeah, doesn't have to be just so. Okay, but the idea is that
I have a question. So you can't flow this thing at the boundary, like along sigma. What happens there?
The boundary moves. The boundary moves with constant speed. You have to boundary.
So you just actually translate that, and in the interior it will be mean curvature flow. I see.
Yes. You don't care about the boundary. The boundary
you just
translates away. You don't see it. Yeah.
I see.
Yeah. And the idea is that, these guys stretch up further and further. They get more and more they more look like cylinders. And the idea is, in the end, sort of, if you look at the evolution kind of here, you nearly don't see the translation anymore, but you only see kind of a normal evolution. And the evolution in this direction is nearly the evolution here of these level sets down here. So the idea will be to take a limit of these translating solutions and in the end get a Brakke flow which is invariant in this Z direction. So we get a limiting Brakke flow which has a translation invariance, and that we can then slice in this direction and get a solution which actually starts from here. So we add this one extra dimension artificially to get smooth solutions, and then we use this to construct a smooth approximation to something weak in the end. So what is the setup here? What is the goal? So here's the goal. Send lambda to infinity. That's the idea. We let them translate. So as you do this, these start translating faster and faster. At the same time, they stretch up higher and higher. And show that m lambda t, and now t, take for example in R plus, because a translated solution, they're defined for all times. They converge to a limit Brakke flow mu t, t greater than 0 on, now we are in Rn plus 2, so one dimension higher, but this flow is translation invariant, which is translation invariant, i.e. what do we want to have? We want to prove that mu t is actually sigma t cross R for sigma t, an n-dimensional Brakke flow in Rn plus 1, which starts where we want to start, where sigma 0 is sigma. And this is how we construct the weak solution. The idea is we have these translating solutions here now. Now, the first thing we will have to prove now are local. Remember, we want to use the Brakke compactness theorem. So we have to prove local area bounds. If we have uniform local area bounds, we're good. Then we can take a limit. Then we have to argue that the limit has actually this translation invariance. And if we've done that, then we have won. Then we just need to prove that this thing, what we get in the limit, still attains the initial data. So that's the goal. Okay. So what I will do now, So any question with this is important here. So happy to answer any questions here now, because that's essential that you understand this idea.
So the goal is to construct a Brakke flow starting from sigma, right?
Yes, in the end, sigma. So we first construct this Brakke flow starting at sigma cross r.
Yes, yes.
Prove that the flow is translation invariant in this extra r direction, and then we can slice.
Okay.
And I saw that there's a question from Stephen. Yeah, no, sigma does not need to embed it. It doesn't need to be embedded. It just needs to be a cycle. So if you want to be very general, you can take anything. Sigma doesn't even need to be regular. Doesn't need to be. You can even do it with non-smooth. You can work with a. You can start with a current. You can flow. You can flow currents with this. That's also a strength. So you can start flowing things which are already irregular itself. Yeah? But it needs to have as a current. It can't have boundary, because you want to write it as a boundary of something. So that's the restriction, because you want to do this minimization procedure. But if you have something immersed, which defines a current, then you're done. Then it works. But the solution, it's a question sort of, does it keep, it could also decide, like, if you have an immersed flow to somehow, like immersed curves, to somehow decide in the middle it wants to split up the immersed curve into embedded curves and decide that's better to do this. Could also happen. Because it's a weak flow, it's allowed to do that. Okay. Now, any other questions? Okay, so then let's use the last 10 minutes to maybe do this first setup here. That's nice. So we do uniform. So we need uniform local area estimates. Now, otherwise, we can't use the Brakke compactness. So I'll draw a picture in the moment. What this set is m lambda of AB is just m lambda A less than Z less than B. And S lambda of C0 is M lambda intersected Z equal to Z0, where we have that the 0 less or equal A less than B. So what is the picture here? Again, a very similar picture to what we just had. Sigma 0. Now here you have your, okay, and so here now, maybe different color, orange. Okay, here is B, here is A. So the shaded region will be M lambda AB, and this here is S lambda of B, and this is S lambda of A, and here in green, this is M lambda. Okay, everyone happy with the picture? And okay, now what we also take new is upward pointing unit normal vector to dm lambda AB, the boundary in m lambda AB. So we blue here. So this is then here new. It's tangent to m lambda, but normal to this boundary, to S lambda. Okay, now here's the computation. It's very easy. So 0 is okay. We go m lambda AB. Now we take the divergence over m lambda of just the constant vector field E. The divergence of that is 0. The ambient derivative is 0. Fine, that's good. But now we can use the definition of the weak mean curvature. M lambda AB. So you get here minus mean curvature scalar product with E. Now we get the two boundary terms, from the more or less the Gauss theorem, E dot nu minus. Now we don't get the same sign because we always took it upwards pointing A E dot nu. Okay. So what is this? Now we just put in the definition, since this solves the translator equation. This is lambda times E perp norm squared plus S lambda of B, E tangential norm minus S lambda of A, E tangential norm. Yeah, that's also fine. Yeah. So what do we get from here? So this is this important thing, yeah, that lambda times E perp squared over M lambda AB plus S lambda of B E tangential is equal to S lambda of A E tangential, just reordering. But you see, this is a positive term. So what does this mean? This means that Z maps to integral S lambda of Z of E tangential is decreasing. Okay. See, that fits kind of the picture. If we go up here, at some point it will sort of curve inwards, and sure, then the tangential part of E will get smaller as you integrate over these level sets, so that you can hope maybe that's a decreasing function, or at least some kind of control. But even get decreasing, now we can estimate that the area of M lambda AB, okay, what is it? M lambda AB, this is E perp squared plus E tangential squared, so it's just 1, yeah. Now we use exactly that formula here. Now we can estimate this from above by 1 over lambda E tangential integral over S lambda of 0. Okay, it's fine now. See, but just because of that formula here. That's this part here. Sorry. This part, see, that's this here. Plus M lambda of AB. And we just keep E tangential squared. Okay. Now, what is this? This is 1 over lambda S lambda of 0 E tangential. But now you see here, what is E tangential? You see E is the ambient derivative of the Z coordinate, and E tangential is the norm of the tangential gradient. And if you remember the core area formula, you can use the core area formula to rewrite that term, to rewrite this as integral from Z equal to A up to Z equal to B of integral S lambda of Z. But now you lose here one power, E tangential dz. Okay, so be really precise here. You should put the right measure in here just to say this is the one-dimensional lower. So this is n plus 1, this is n-dimensional dz, okay? Now, okay, but this we can estimate now. This is less or equal than lambda inverse plus b minus a. And now, remember, this was a monotone function here, times s lambda of 0, E tangential, which is less or equal to lambda inverse plus b minus a area of sigma. Which is great, yeah? See already, this is sort of like, in some sense, it resembles already mean curvature flow. Because you see, more or less, the area of your initial surface controls the areas at later times. Because you think like going up on this translator is controlling the area on later times. Yeah. Okay, but what does this mean? This means like in any finite slab here, yeah, we have, see, this is just controlled by sigma. So independent of, if you make lambda big, that goes to 0. So we have uniform control independent of lambda. This means for the whole Brakke flow, for this whole flows here, huh? So these flows, which this m lambda t, they have locally uniformly bounded areas. We just have them controlled in these slabs. So what do we know now? Huh? So what do we do next time? What we're able to do, we can use compactness. We get a limiting Brakke flow. Now what do we want to show? We want to show then that this translation invariant. And that it attains the initial data. Okay. And the other points which we'll cover on Thursday will be the monotonicity formula, the definition of entropy here for these flows, and how we can construct tangent flows. Again, this uses compactness. So this gives them the first order singularity models at singularities. Okay, I think we have 5 minutes left. Are there any other questions? Something in the chat? Sorry, I can't hear it.
In the co-area formula you use, I didn't get why the square disappeared.
Yeah, this is because we use the co-area formula. You see, the co-area formula says if you have a submanifold, yeah, M of any codimension, and you have an ambient function f, yeah, then integral tangential gradient of f is, you can write this as minus infinity to plus infinity integral f equals to z intersected m, 1, or you can actually integrate a function g here, g dhn minus 1 if this is n-dimensional. That's the co-area formula. Okay, and you see here E tangential is exactly the tangential gradient of the z coordinate. So we lose one square here, and then we can use the co-area formula in this form. And g is exactly the second factor here. Does that help?
Yes. I forgot the gradient.
Yeah. There were some more questions in the chat. What is F is E scalar product on M? That's not really clear to me. Yeah, okay, that's the Z coordinate. That's F here. Yeah, that's just the Z coordinate. E scalar product is just the Z coordinate. Exactly, that's right. Yeah.
Can I ask a question?
Yeah, sure.
So all this estimate works just for a stationary point of the functional.
Yes.
Right. So if you use minimizer or stable point of elliptic regularization to approximate mean curvature flow, can we say more about the proximate?
You mean you want to use stability or minimization?
Yeah.
People have tried. The problem is in the limit, this minimization degenerates. You can't, yeah, you can try, but yeah, I've tried. I guess many other people have tried too. Yeah. Somehow, when you take this limit lambda going to infinity, this information you get out of stability, just take stability as a weaker information, that somehow disappears. So it's a good question. I guess many people have tried if you can get some information. In some sense, you're right. Critical points should be enough. This should work. If you want to construct something, usually you construct by minimization. Yeah? But I don't see, at least I haven't seen, it would be nice to somehow get some property into the limit by using kind of stability before or something like this. Yeah?
All right.
Very good question.
And another question is, so can we see directly from the elliptic regularization the singularity behavior of mean curvature flows, like its tangent flow or other limit flow?
Not really. I haven't really seen that. So it's really going to the limit. You can do a diagonal sequence, yeah, but I don't see that you get more information about this. You can get some properties. We won't be able to discuss it like you can, for example, this property called it, if you might have heard it, like unit regularity or cyclic mod 2 or stuff like that. There you can prove, like, if you prove that, for example, that a certain property is preserved under weak convergence of Brakke flows. Give any property of, and you make sure that in elliptic regularization your approximizers have that property. Then the flow in the limit will have that property as well. So this has turned out to be very successful, because you can sort of like construct now weak solutions with additional properties. But you have to first prove that you have a certain property and that property is preserved under weak convergence of Brakke flow. But this then makes it possible to somehow get rid of some bad pathologies for Brakke flow, or at least deal with them in some sense.
Like the non-uniqueness, or
in some sense, unit regularity somewhat says you avoid. So in some sense, says you can't have sudden vanishing where the flow is smooth and unit multiplicity. Then you can't just vanish out of no reason. If your flow is smooth and has multiplicity 1, then it can't just vanish. That's unit regularity. And that you can prove is preserved under weak convergence. So you can somehow say you can't have a flow which is smooth, multiplicity 1, and then just disappears.
Mm-hmm.
But that's interesting. You need some properties. You can't do it always. For example, like for this network flow, if you've seen this with like triple junctions, there you can't set this up. There you have to allow to just even multiplicity 1 bits to just disappear. But if you flow like hypersurfaces or nice currents, you can work with unit regularity.
Okay, right. Thank you.
Any other questions?
Not on our side.
So you say again?
We have no questions in the room, actually.
Okay, good. Okay, then I guess I'll see.
Thank you, Felix. And if I remember well, we meet again on Thursday.
Yeah, Thursday morning, I think. Yeah.
Thursday morning, yes.
Yes. Okay. Good.
Okay, thank you very much.
Have a good time.